Good morning, everyone. I'm pleased at least to see a reasonable crowd even in the very last day, right? Um, let's the authors have spent a lot of time working on these papers, and getting it accepted. So we should give them our full attention and interest. So this is a session on SSDs, which is somewhat broad. Um, And we have 5 papers in the session. The first paper is called AERO, Adaptive Erase Operation for Improving Lifetime and Performance of Modern NAND Flash-Based SSDs. Multiple institutions involved. This paper is going to be presented by Sungjun Cho, who is a fourth-year PhD student at POSTECH. He is currently serving as a visiting scholar at UIUC. His interests are in memory and storage systems, co-design, and so on. He's on the job market.
Okay, thank you for introduction. Hello, I'm Sungjun. I'll be presenting our work, AERO. So to begin with, here's a summary of our work. Long and fixed latency of erase operation degrades SSD lifetime and I/O performance. So our goal in this work is to minimize the negative impact of erase operations. To achieve the goal, our key idea is to apply erase latency to be just long enough to reliably erase block. Based on our evaluation, AERO improves lifetime by 43% and reduces retail latency by 26%. I'll start with a brief background on NAND flash memory. In NAND flash memory, a set of flash cells from a NAND string that is connected to a bit lines. NAND strings of different bit lines compose a flash block, and flash cells at the same vertical locations are connected to word lines so that every cell in the same word line operates concurrently. To write data, program operation applies high voltage to target word lines to inject electrons into cells. In contrast, erase operation applies high voltage to target flash block to eject electrons from every cell in a block. Because erase and program operation only eject and inject electrons respectively, flash cells need to be first erased before programming. Now let's see how erase operation works. It consists of 2 steps, erase pulse and verify read. Erase pulse applies high voltage to a target flash block for a fixed latency, here 3.5 milliseconds. After that, verify read checks if a block is completely erased or not. If so, erase operation finishes after 3.5 milliseconds. However, erase operation with long latency and high voltage physically damages flash cells, limiting SSD lifetime. Also, its long latency can often delay user requests for a long time, increasing retail latency. Even worse, as the number of program and erase cycle increases, it becomes more difficult to erase block. As shown in here, after first erase pulse, some of cells can be insufficiently erased. To handle this, it is common practice to repeat erase pulse and verify read until the block is completely erased. This is called incremental step pulse erasure. This graph shows how the number of erase pulses increases depending on P cycle. As you can see in this graph, as P cycle increases, the number of erase pulses also increases. For instance, at 5K P cycle, every block requires at least 4 erase pulses to completely erase block, and thus erase latency increases up to 70.5 milliseconds. This means that as P cycle increases, the negative impact of erase operation become much higher. Our key observation in this work is that even at the same P cycle, the total erase latency significantly varies across flash blocks. And even for the blocks with the same number of erase pulses, again, erase latency significantly varies across flash blocks. So if we use fixed latency for each erase pulse, many blocks will be over-erased, meaning that high erase voltage is applied for a longer time than necessary. So fixed latency of erase operation can cause unnecessary damages and delays. Thus, our goal in this work is to minimize erase latency to improve lifetime and performance. Let me explain the problem again. With a fixed latency, erase operation can cause unnecessary damages and delays. Instead, As you can see on the right side, our key idea is to dynamically adjust erase latency to be just long enough to reliably erase block. But the key challenge is how to accurately predict erase latency, because even at the same P cycle, erase latency varies across flash blocks as discussed before. To estimate erase latency, we propose fabric count-based erase latency prediction called FELP. As I explained, verify read checks if a block is completely erased. It does so by counting the number of unerased cells in each bit line, which we call fabric count. We hypothesize that the lower the fabric count, the lower the latency will be for the next erase pulse, because the fabric count would increase as more cells are insufficiently erased. So if we use the fabric count from the previous verified read, AERO can dynamically adjust the latency of the next erase pulse. However, FELP is not perfect yet. This is because the verified read does not occur before the first erase pulse, which means AERO cannot reduce the latency of the first erase pulse. As you can see in this graph that I brought again, in early SSD lifetime, most blocks are completely erased in the first erase pulse, which means it is important to optimize the first erase pulse. We address this by splitting the first erase pulse into two parts, shallow and remainder erasure. To be specific, AERO first performs shallow erasure with a short fixed latency here 1 millisecond and counts the fail bits from an additional verified read. Based on the fail bit count, AERO can dynamically adjust the latency of the remainder erasure. Here, even if AERO performs an additional verified read, its latency is marginal, which is about 80 microseconds. As the second optimization, AERO reduces erase latency more aggressively. As you can see on the left side, basically, AERO is designed to always completely erase a block. Instead, we found that in many cases, it is fine to incompletely erase a block. So for example, as you can see on the right side, AERO can further reduce erase latency by allowing unerased cells in the splash cells in the block. But this may introduce additional bit errors. However, we found that these errors caused by the fabric count can still be corrected by error correction code inside modern and splash-based SSDs. As a result, incompletely erased blocks are still reliable to use. We validate the feasibility of AERO using real 3D NAND flash chips, and please refer to our paper for more details. Now, let me explain the implementation. We extend the conventional FTL with two new data structures. First, shallow erasure flags tell if a block requires shallow erasure. Second, erase timing parameter table tells the minimum latency of the next erase pulse depending on the number of erase pulses performed so far and the fabric count from the previous verified read. FTL uses two commands to adjust erase latency here. First, FTL obtains the fabric count from a flash chip using the get feature command. Second, FTL sets the erase pulse latency using the set feature command. So to perform erase operation with shallow erasure flags, FTL first checks if a block requires shallow erasure. If so, it sets the latency to 1 millisecond and perform shallow erasure. If not, it skips shallow erasure and directly performs the first erase pulse with fixed latency. Here, this is 3.5 milliseconds. Now, after verified read, FTL obtains the fabric count from the flash chip and determines the next erase pulse latency by calling the table. Finally, it sets the latency to perform the next erase pulse. Here, this is remainder erasure of the first erase pulse. If FTL fails to reduce the latency of the first erase pulse, it updates the shallow erasure flags to false. We evaluate AERO in two ways. First, for each lifetime impact, we measure the maximum P cycles using real 3D NAND flash chips. For each performance impact, we evaluate with tail latency by extending MQSIM simulator with real device characterization results. We compared three erase schemes. Baseline uses fixed latency, and both AERO conservative and AERO use dynamic latency, while we apply aggressive reduction optimization only for AERO. This graph compares how the average maximum errors increases with P cycles in each erase schemes. we assume the maximum correctable errors of 63 bits. So once low bit errors exceed the maximum correctable errors, the device reaches the end of lifetime. In the case of error conservative, errors slowly increases because it reduces the damage to flash cells by reducing erase latency. Thus, it can improve lifetime by 30% over baseline. In the case of AERO, errors are significantly higher than other erase schemes. This is because AERO further reduces erase latency by getting each errors close to the maximum. Here, even if errors are high, please note that modern SSDs can still correct these errors using error correction code. In turn, AERO can improve lifetime by 10% over AERO conservative and 43% over baseline. So we can conclude that AERO can significantly improve SSD lifetime. We also evaluate for-line read latency. At 0.5 kp cycle, AERO reduces read latency by 26% on average. To be specific, we observe that workloads with various read and write ratio can benefit from AERO. Here, AERO conservative and AERO show similar performance because erase latency variation is not high at these points. Considering that most blocks only require the first erase pulse at 0.5 kp cycle, we can conclude that shallow erasure is effective in reducing read tail latency. At 2.5 kp cycle, we can observe that aggressive reduction here can further reduce read tail latency compared to AERO conservative. This is because as P cycle increases, the impact of latency variation increases. So we can conclude that aggressive reduction also is effective in reducing read tail latency. We also deal with many other aspects of AERO in the paper. To conclude the talk, I summarize the work again. In modern NAND flash-based SSD, long and fixed latency of erase operation degrades lifetime and I/O performance. To handle the problem, we propose 3 key ideas. First, FELP allows to dynamically adjust erase latency. Second, shallow erasure enables reducing latency of the first erase pulse. Third, ECC available in modern SSD can enable further reducing erase latency. Based on our evaluation, AERO can improve lifetime by 43% and reduces read tail latency by 26% on average. So if you are interested in more details behind AERO, please refer to the paper, and thank you for your attention.
Saurabh Kadekodi from Google. Nice talk. I have a question about the complexity of wear leveling in the FTL because of now different erase blocks being erased to different degrees.
Yes.
And you showed read performance, but does it complicate the write path and takes more time to find which blocks you're supposed to write to?
So what are you considering about wear leveling?
That wear leveling, it is expected that all blocks will wear evenly, and that if you are going to erase them in the same way, they will probably wear evenly. But now you're erasing them differently, so they will wear unevenly. And what is the consequence of that? Have you thought about that?
So basically, historically, wear leveling is done by counting the program erase cycles. But here, we apply erase operation by counting the fabric count. So because basically, the fabric count means that if the fabric count is same for each flash block, it means that they have a similar lifetime. So in that case, we can, by counting the fabric count and erase operation history, we can match the wear leveling balance between different blocks.
I thought of the same response, but then towards the end of the flash lifetime, wouldn't everything become long latency?
Yes, as I said, as I show you before, the graph here. Sorry. Here, as P cycle increases, the number of erase pulses increases. This is because the flash blocks become much difficult to erase a block as its lifetime close to the end of lifetime. So the erase latency becomes much higher than before.
Any other questions? Okay, now let's thank you. The next talk is going to be given by Sujay, who's a PhD student at Wisconsin. His research interests are in operating systems and computer architecture, and he's been working on problems related to memory and storage.
Just give me a minute.
He's had laptop problems, so.
My computer rebooted for some reason. Yeah, it's booting just. Or can I connect my phone? Okay. All right. Sorry about that. Sorry to keep you waiting. Thanks for that introduction. Thank you all for coming to my talk. I'm really excited to talk about our work called Bypass D, which is a new interface we built for accessing modern SSDs. I'll start off by giving a quick overview. So modern SSDs are really fast. We have devices like Intel Optane SSD that offer latencies less than 10 microseconds. While this is great, it's sad that the software we use to access these devices add a lot of overhead. Now we see that in some cases, the software can be as much as 100% overhead. Now we observed this and we wanted to solve this. So we proposed a solution called Bypass D, where we make two key design choices. The first is we let applications allow to access the device directly from user space by bypassing the kernel. So by this, we achieve lower latency. And second, we want to ensure that the device can be shared across applications. So we offload some permission checks to the hardware. And by doing so, our evaluation showed that we could eliminate most of the overheads. As you can see, the orange bar is really small here, and we can achieve really good performance. Okay, hopefully I gave you a flavor of what this talk is going to look like. So I'm going to talk more about the problem, motivate why we need a new I/O architecture, then talk about Bypass D, its goals, and how it achieves them. And finally, we look at some results from our evaluation. So just like every other technology, there has been significant advancements in storage. In the past few years, we have had devices like Samsung ZSSD, Intel Optane, which offer really low latencies. Unfortunately, the conventional approach of accessing these devices, through the kernel, where we incur a context switch and go through multiple layers, it's pretty slow. So here I just show you a latency breakdown of a 4 kilobyte read. So you can see that 50% of the time is attributed to the raw device latency, and then there's 50% overhead. So this is quite significant. Now, we are not the first ones to identify this problem. A lot of researchers have seen this problem. So some have tried to solve this by proposing optimizations to the kernel software stack. But the problem here is that you still have to pay some cost. For example, you can't get rid of context switch and you have to pay the cost of it. So others have tried a different approach So they move the file system into the user space. So those of you who are familiar with SPDK might appreciate how SPDK is able to achieve low latency. But the problem here is that these user space solutions, they don't allow the device to be shared. Now, what do I mean by this? So let's just take an example here. So, in systems today, if you have such files and such users, the kernel will ensure that user one can only access bar.txt. Like the kernel will not allow user one to open foo.txt. But unfortunately, when you're using a user space solution like SPDK, there's no entity that performs these checks. The user process can access any block or any file on the device. So sharing becomes really difficult. Now there's a third class of solutions, which I call device file systems, where they move the entire file system or parts of it to the device. Now this solves the two problems, but then it introduces a new one, which is that it needs reinventing the file system structure, and that it is constrained by the resources that the device has, like the CPU and memory. So ultimately, we make this observation. We said, hey, there is no solution that achieves low latency, enables device sharing, without making significant new changes. So keeping this in mind, we wanted to build a solution. And just like all of you, there were a lot of brainstorming sessions. And we observed something during our discussions. We said, hey, you know what? When devices want to perform DMA to memory, either during a read or a write, they have to go through the IO memory management unit, or the IOMMU. The IOMMU basically translates the virtual address of the buffer to the physical address. We made another observation. We said, hey, in modern processors, these IOMMUs, they can access the process page tables. So previously they had to used a separate set of page tables, but now they can access the page tables of the processors. So we said, hey, why can't we just use the IOMMU to perform some checks while applications access the device directly from user space? So using this, we built BypassD. So on this slide, I show you the main components of BypassD. There's the file system, the user lib, and the IOMMU. So to make sure that we are not reinventing the file system, we retain the file system as is in the kernel. But then, as I mentioned, for low latency, BypassD allows direct access from user space. So now it does not have to go through the kernel, and so the software overheads are much lower. So for this, we adopt a split architecture. So what I mean by split architecture is that data operations are handled directly from user space, but metadata operations such as append or fallocate or things like that have to go through the kernel. And second, I mentioned that we want the device to be shared, and so we enforce this security and this permission checks in the hardware by offloading some of these tasks to the IOMMU. Now, to better understand how we do this, I'll use an example. So if a process wants to access files directly, what it'll initially do is it'll set up this, what we call the direct access path. So this involved, setting up NVMe queues, buffers in the user lib, and more importantly, it involves setting up the permissions for the file. And I'll discuss more about this in the next slide. And once that is done, the applications can access the device directly. And as I said, when this happens, the SSDs interact with the IOMMU to verify that the access is permitted, and then voila, we are done. So let's go deeper into each of these steps. So I said, that we have to set up permission. So in BypassD, we propose a new system call called fmap. The key idea here is that the application expresses intent to access the file directly. So it's saying to the kernel, hey, I want to access this file directly. Now, when it does this, what the kernel does is create this new thing we call the file table entries. So file table entries are very similar to page table entries, except that instead of storing the physical frame number of a page in memory, they store the block address of something in the device, of the corresponding to the file in the device. And once the kernel sets up these file table entries for a file, it'll attach that to the process page tables at some virtual address, which we call the virtual block address. Now, once this entire tables are set up, applications can then access the file using the virtual block address instead of the logical block address. So now in bypass D, when you're issuing NVMe commands, you don't use the logical block address, but you use this new virtual block address. Now, devices can't make sense of the virtual block address because they work with logical block addresses. So they communicate with the IOMMU to get it translated. Now, recall I told you that the IOMMU can access the process page tables. So it goes back to the process page tables, accesses the file table entries, and figures out the logical block addresses corresponding to the virtual block addresses. And once that is done, the IO access can complete. So this is basically the essence of how bypass D supports sharing. So it means like if you have if the IOMMU is able to translate the address successfully, it means that the file table entries were valid, which means that the kernel permitted the process to access it. So, and if the IOMMU cannot translate, it means the file table entries were not set up, so the process cannot access that file or block directly from user space. Now, nothing comes for free. There's always a cost. So in bypass D, the cost comes during FMAP because you have to create these file table entries and attach them to the process. And this can get quite costly if you have to keep doing it every time. So to optimize this, we propose to cache or to pre-populate these entries because the blocks corresponding to a file does not change frequently. And then when processors want to access these files, we attach them quickly in like O of one time without a lot of overhead. And now there are a lot more details to how bypass D works, how it handles different system calls, different metadata operations, multiple writer scenarios. But I won't go into the detail in this talk. For all of that, please do refer to the paper or reach out to me. I just want to talk about some of the results we have gathered. So we ran experiments on a real system with Optane SSD, but unfortunately, we can't make changes to the IOMMU, so we had to emulate that. To do that, we ran some experiments. We measured like the PCIe latency between the SSD and the host or the IOMMU, and then also captured the page table walk latencies of the IOMMU. We saw that this could be anywhere upwards of 550 nanoseconds. We modeled that in our system as delays. We use 3 classes of workloads. We use micro benchmarks, some real-time workloads, and also some research prototypes from past works. But in this talk, I'll mostly look at some micro benchmarks and wired tiger. The first experiment is quite simple. We just wanted to measure the random read latency. We use a single thread on a single file, reading different random blocks continuously. So on this graph, I show you the latency along the y-axis. The lower is better. And along the x-axis, I show different block sizes and for different approaches. The blue bar shows the raw device latency and the orange bar shows the software overheads. As you can see, for the Linux baseline, for small block sizes, the overheads is quite significant. It's almost equal to the device latency. We also evaluated SPDK, the user space solution I mentioned, and as expected, the overheads are significantly lower. You see that most of the time is spent in the device and nothing in the software. And bypass D performs very similar to SPDK with very slight increase. So this experiment basically shows that bypass D is able to achieve the low latency that SPDK can and achieve sharing at the same time. We also did an experiment on multi-threads. The graph is very similar, but along the x-axis, I show the number of IOPS, and I write the number of threads for each data point. So the blue line is for Linux. As expected, with SPDK, the latency goes down significantly and the IOPS increases. And bypass D is very close. There's, again, as I mentioned, slight increase in latency, which can be attributed to the virtual block address translation overhead. And we see that bypass D is able to achieve, again, similar performance to SPDK. Last, I I want to discuss some of the results from our real world workloads, WiredTiger. So WiredTiger is a storage engine that's quite popular. It's used in MongoDB. We populated it with 1 billion key value pairs. And then we ran different YCSB workloads. The blue line corresponds to Linux and the green line corresponds to our solution BypassD. As you can see, on average, for most workloads, BypassD outperforms the Linux baseline. You might observe that BypassD does not improve performance for YCSB-D. That is because it's a write-intensive, append-intensive workload, and metadata operations are routed through the kernel, so we can't really benefit from direct access. With that, I just want to summarize. So hopefully I motivated that, modern SSDs are really fast, and the software stack we have to access these are quite slow. And so we propose one solution to this problem called BypassD, where we used some inspiration from virtual memory. We virtualized the block addresses. We created this virtual block addresses and used the IOMMU to translate this, thereby enforcing some protection checks in the hardware. And from our evaluation, BypassD can outperform Linux baseline by a significant margin. I just want to take this opportunity to thank my collaborators. This work wouldn't have been possible without them. I'm also happy to share that BypassD is open source. It has been tested, verified. I encourage all of you to try out BypassD with any storage intensive applications that you have. You might see some good numbers. Please do share them with us. And with that, I can take questions if I have time. Thank you.
Hello, nice talk. I'm Sungjun from POSTECH. I wonder if your work can still be extended like a RAID file system or network file system, because in these days it's very common. So yeah.
So if I understand your question, you're asking if I can work with different file systems?
Yes, but basically most file systems are implemented in the kernel space, but you are trying to move them into the user space.
No, so in BypassD, we don't move the file system from the kernel. We reuse them as is, and that's one of the goals for BypassD. We don't want to, rewrite file systems because that can be messy, that can be tricky. So we want to reuse the file systems in the kernel space, and BypassD can work with most file systems that exist today. There are some situations where it won't work, like log-based file systems. But for most others, we can work with any file systems. Yeah.
Okay, thank you.
Cool. Thank you.
Hi, I'm Sungjun from UC San Diego. I'm wondering if BypassD ever uses the TLB in IOMMU to mitigate the IOMMU memory access latency?
Yeah, I think that's a good question. So the question is, the IOMMU has a IOTLB, and can that be used to reduce the cost of translation? So we didn't want to use the IOTLB for one reason, because most applications that go to storage don't have reuse. You read a block and you move on. You don't keep reading the same block over and over. So there is no reuse or temporal locality. So there is no real benefit from using the IOTLB.
So so the IOMMU latency always occurs for the every.
Yes,
IOTLB.
that is correct.
Fair enough. Thank you.
Thank you.
That was a segue into my question, actually. So isn't this creating a side channel, right? I mean, you have dealt with the protection problem, but if there are two user processes sharing this IAMMU and going through that, now I can actually, exercise requests that would, cause more misses because there's no TLB and leak information that way, right? So isn't this a problem?
It could happen, I guess. I haven't thought about this in detail, but yeah, I guess side channels are always possible when you are sharing and there is variation in performance. So yeah, it could happen, but I don't have a solid answer for you. Sorry. All right, thank you.
Oh, hello everyone, I'm Yu Hongwen from China. I will introduce our work about eliminating storage management overhead of data application over SSD arrays through a hardware-software co-design. Duplicate data is widely present in current storage systems. For example, there is up to 68% and 97% duplicate in primary and backup storage system respectively. Duplication, or DDAP for short, is able to remove duplicate writes and thus reduce storage cost and SSD wear. It has two main components: duplicate and duplication and the storage management. First of all, data streams are split into small-sized data chunks, such as 4 kilobytes. And then they are hashed to smaller size fingerprints as their unique identifiers. By comparing fingerprints, duplicate data can be identified. Secondly, storage management performs address mapping between user storage addresses and device storage addresses. It writes non-duplicate to devices or update metadata to remap duplicate to the previously written data chunk, such as the DUP mappings and the reference counts of each data chunk. Besides, the garbage collection is required to recycle unreferenced data and their fingerprint index. However, DDAP brings significant extra I/O overhead to persist the metadata, and if the metadata is partial cached in host memory, it needs to be loaded from and written back to SSDs frequently. As shown in the figure, we observed several to more than 20 times of I/O amplification due to metadata, half of which is due to mapping metadata. The DDAP GC is performed to clean invalid fingerprints and the storage space. It aggravates I/O overhead since it brings metadata updates and can block user I/O. In particular, there are trade-offs between SSD GC and DDAP GC. As we can see figures in the red box, if DDAP GC is frequently triggered, SSD GC overhead is small. But if DDAP GC is not triggered frequently, SSD GC overhead is high because unreferenced data cannot be invalidated in time and is regarded as valid in the SSD. Existing works propose to integrate DDAP into the SSD FTL called intra-SSD deduplication, as shown in the figure B. To leverage SSD's inherent address mapping and GC capabilities to achieve DDAP, thus removing the function redundancy shown in the figure A. However, SSDs can only support device-wide storage management, which does not match with the array-wide DDAP requirement. In the right figure, we can see in the scenario of an SSD array, intra-SSD DDAP loses most of the DDAP opportunities. The traditional block layer DDAP suffers significant metadata overhead due to the redundant storage management, while the intra-SSD DDAP does not support array-wide deduplication. Our goal is to enable the offloading of array-wide DDAP storage management to the multiple SSDs in the array. In the hardware, we strengthen SSD's storage management ability for supporting array-wide remapping. In the software, we design a lightweight DDAP engine on the host, which keeps the fingerprint index while the storage management is decoupled and offloaded into the SSD array. Specifically, traditional device-wide SSD FTL cannot manage array-wide cross-device mapping, as shown in the left figure. Even if LPNK is a duplicate of LPN0, it is in SSDK and cannot map to PPNX in SSD0. To solve this problem, we propose a novel array-wide remap SSD called ARM SSD, which extends FTL with an additional remote mapping table for array-wide address remapping. The remote mapping table in each SSD covers the address space of the other SSDs in the array. So each SSD has a global view of the array address space. For example, as shown in the right figure, the DAB engine finds that LPNK is a duplicate of LPN0. Although LPNK is located at SSDK by default in the RAID layout, it is remapped to SSD0, where the duplicate data is stored. It's expensive to maintain a large remote mapping table covering the array address space for remapping. We use N2-1 direct mapping to map the array address space to a small remote table in each SSD. Experiments show that expansion of 20% to 50% to local mapping table size is sufficient, and the DDAP loss is small. Besides, we found that decoupling storage management from the DDAP software leads to a data inconsistency problem. Traditional DDAP engine allocates each unique fingerprint an physical page number, PPN. These key value pairs are recorded in the fingerprint index metadata and guarantee data consistency. Data writes or DDAP updates the mappings between logical page number and physical page number. However, after offloading DDAP mappings, there is data inconsistency in the fingerprint index. As shown in the right figure, when the data of LPNX is updated from data A to data B, both the fingerprint A of the old data A and the fingerprint B of new data B all map to an LPNX, and while this LPNX maps to data B, which means fingerprint A wrongly maps to data B. This data inconsistency leads to wrong DDAP and data loss. We propose a version-based fingerprint verification scheme to solve this problem. By recording the data version of each LPN and comparing it with the data version of fingerprint, invalid fingerprints can be identified and wrong DDAP can be prevented. Overall, our solution is a hardware-software core design involving block layer DDAP software, RAID controller, and SSD hardware. More details can be found in the paper. We implemented a prototype by modifying the Linux DMDDAP module, software RAID module, and the FAMU SSD emulator. Compared with the traditional block layer DDAP system, DMDDAP, our ARM DDAP removes the DDAP GC and performs real-time SSD GC, thus keeping data footprint and SSD GC overhead low. Removing DDAP mappings reduces metadata footprint by 43%, alleviating cache contention and thus reducing metadata I/O by 59%. Besides, average latency and the write amplification is reduced by 54% and 74% respectively, and the LPS performance is improved by 120%. Compared to DDAP SSD, our solution achieves higher DDAP ratio from 12% to 45%. We have also conducted extensive experiments under different system configurations and workload characteristics. Our solution achieves up to 2.7 times higher LPS and up to 92% of read amplification reduction. In the workload with 90% duplicate, our solution loses less than 9.4% dedup ratio with only 20% expand large with only 20% table expansion. When the workload duplicate ratio decreases or the remote mapping table expands larger, this dedup loss will be lower. In summary, modern storage systems cannot fully utilize the powerful SSD hardware performance due to high software overhead. One way to solve this problem is through hardware and software co-design. In this paper, we showed how this idea can be achieved to optimize the deduplication system performance. My report is over. Thank you.
Hello, Jisung from POSTECH.
Hello.
Thank you for a nice talk. I want to ask more about the overhead of extending the mapping table. Because if I remember correctly, your proposal increases the size of a mapping table inside SSD
Yes.
from 20% up to 50%, but I wonder if it is acceptable. So my first question is, where did you assume the mapping table is stored? So is it stored in internal DRAM inside SSD or NAND flash inside SSD?
We stored in DRAM.
DRAM.
Yeah.
But if as far as I know, already commercial SSDs are suffering from the shortage of DRAM space because mapping table size is really big already. So I wonder if the increase in mapping table size is acceptable.
Yes, this is the trouble in this idea, but we want to say that we won't expand too large the table. As we can see, only 20% the table expansion is also sufficient. So
Okay.
It's a configurable parameter.
Yeah, but if as far as I know, a typical commodity SSD needs like 0.1% of DRAM. So the DRAM as large as 0.1% of SSD capacity. For example, typical 1 terabyte SSD are using 1 gigabyte DRAM, but most of the space is already occupied by the mapping table.
Yes.
Yeah, but increasing 20% is somewhat could be quite expensive because it needs increasing the internal DRAM of SSD by 20%. Okay.
In our design, we actually need more DRAM in SSD to maintain the remote mapping table. But we want to say that why we do this design is from the overall architecture overhead, since we reduced from the system oversight, we reduced the deduplication mapping table. So from the view of our system, our DRAM requirement is decreases. But surely the device is required more.
I think you want to say your overall benefits outweigh the costs, right?
Yeah.
Okay, thank you.
Let me ask a more philosophical question. See, one of the reasons we have, multiple flash devices, apart from performance, is reliability, right? Now, if you start deduplicating across these, what is the consequence on reliability?
Sorry, due to my poor English
No,
listening.
what I'm saying is now data is in only one place, right?
I'm sorry.
A block now is in only one device
One
because
device.
you deduplicate it. Right?
Okay, yeah.
So if that device goes bad, it affects more blocks,
Yeah.
right? So I'm just wondering, have you had a chance to look at what happens to the reliability when you do this array-wide dedupe?
Sorry, I truly
Okay,
misunderstand.
that's okay. Take it off.
Sorry.
So this paper is called Basic Diagram, Interested in Android IO Stack. This will be given by one that since it's a remote class, we want to have an opportunity to interact questions. So you will make up some of the time. If you have any questions, you can email the author.
Hi, I'm Yuan Zhang, and I will present our work, Lazy Barrier, which is about achieving order-preserving write. And this is the work from Samsung Electronics. So what is order-preserving write, or OPW? Briefly speaking, OPW can guarantee the storage order. Before giving a more accurate definition, let's see an example. This code reads data A and then data B. So is A stored in the device ahead of B? The answer is uncertain. When write system call returns, data A and B may be still in page cache. In addition, block layer and the volunteer cache in the device also affect the order. So data B may be positioned ahead of A, even A is written first. Now we can give an accurate definition for OPW. It guarantees that write order equals persistence order. Storage order is very important in computer systems such as Android smartphone. For file system, database, and apps, a certain storage order must be promised. The basic way to guarantee storage order is fsync. For example, we interleave fsync between write A and write B. Fsync transfers data A to the storage device and waits for the DMA transfer finish. After DMA, data A may be still in device volunteer cache, so fsync needs to send a flash command to persist all the cached data, including data A. Therefore, A is persisted ahead of B. However, fsync is too slow, so fbarrier was proposed, and it solves the order issues in file system and block layer without just waiting, and uses BWC to replace flash command. BWC guarantees that the device persists commands in group 1 ahead of commands in group 2. It has been standardized in eMMC and UFS, both of which are widely used in mobile device. fbarrier is similar to fsync but faster. The difference is that when fbarrier returns, data may not be persisted. The high performance of fbarrier is attributed to 2 points. It needn't wait for DMA to complete and uses the lightweight BWC instead of flash command. This is the 4 KB I/O throughput measured in Android smartphone. We can see that fbarrier achieves much higher throughput. In no bear mode, fsync doesn't send flash command, so the throughput is higher than POSTECH by over 4 times. But there are still some limitations of fbarrier. The first one is BWC inflation, which means the number of BWC increases linearly with the number of threads calling fbarrier, and it leads to low scalability on multiple cores. Second, fbarrier is designed for ext4, that is a journaling file system. But now Android smartphone uses a log structured file system named F2FS in data partition. Third, fbarrier solves the order issue in single queue block layer. but multi-queue block layer has completely replaced it from Android 11 and Linux 5. To address the limitation, we propose lazy barrier. It includes lazy issue, barrier, and barrier scheduling. To introduce lazy issue, let me explain BWC inflation first. D means user data, B means BWC, and M means metadata. Assuming thread A and B read some data and call F barrier in the same time, in the common file systems, the user data must be persisted ahead of metadata. So BWC is interleaved between them. The second BWC guarantees the metadata are persisted ahead of the future user data. So each thread issues two BWC. But actually, a single BWC can guarantee all the user data are persisted ahead of all the metadata. So how to design an algorithm that guarantees the storage order with the minimum number of BWCs in any condition? To accomplish it, we regard F barrier's control flow as a state machine. Initially, the thread stays at P0. After it dispatches user data D, it moves to state P1, and then dispatches a BWC and moves to P2, and so on and so forth. F barrier has two problems. It immediately dispatches BWC of B or M, and each thread manages BWC locally. Namely, it controls its state transition exclusively. Our solution to these problems are greedy and global. The greedy means we delay the dispatch of BWC to the deadline. The first deadline is the dispatch of M, so we remove the original state P1 and change the state from P1 to P2 when the thread dispatches the BWC and M. The global means reducing BWC. Assuming thread B also reads some data, when its metadata are ready, the BWC dispatched by thread A can also meet thread B's demand, so thread B can directly dispatch the metadata without another BWC. The words above can be translated into this algorithm. Note the state machine also changes a little. The thread state is P1 and M is ready. The thread dispatches BWC and M sets its state to P2. The key step is that other threads reset their states to P0, which implies that they needn't dispatch BWC. The second deadline is when the next user data comes. For example, thread A wants the string hello to be persisted ahead of word. Then a BWC must be dispatched after the metadata of hello and before the user data of word. Similarly, we can get the algorithm, and the state machine needs some correction. We further simplify the state machine and get the algorithm, which can guarantee the persistence order with minimum BWCs. This issue is deployed in the driver. You can read our paper to get the reasons. The second issue is to support OPW in F2FS. For this purpose, we introduce add barrier. We add two fields, PID and add barrier in IO request. F2FS calls user data and data block. When calling add barrier, the thread fills PID and barrier, and then submits the data block. The driver gets the data block, changes the thread state to P1, and dispatches the data block to the device. After that, F2FS immediately writes metadata named node block. The process is similar. According to lazy issue, the state keeps unchanged, and the driver must dispatch the BWC before the node block. After node block is dispatched, add barrier returns. If the thread writes some data later, the driver will dispatch a BWC before dispatching the new data block. However, I just ignored block here, which may lead that node blocks arrive at driver ahead of data block. To solve it, we propose barrier scheduling to achieve in-order processing in multi-queue block layer. Assuming the thread runs on CPU 0 at the beginning and writes data block, but a context switch occurs. The kernel rescheduled the thread to run on CPU N, and the thread continues to write node block. This leads that the node block enters a different hardware queue, so the node block and the BWC may be transferred earlier than data block. Barrel scheduling addresses the problem by adding extra FIFO queues and inserts OPW requests in the nth queue. N is decided by PID, so the OPW requests from the same thread enter a same queue. And barrel scheduling also merge normal requests in legacy queues into OPW requests, if possible. With these techniques, Lazy Barrel provides high performance OPW. We evaluate our proposal in smartphone and server. The UFS device supports BWC when no SSD supports it, so we simulate BWC in server workload. We mainly compare our AdBarrier with NoBarrier FSync and FBarrier. We first use FIO to bench the 4 KB performance. AdBarrier shows better throughput than NoBarrier. Compared with FBarrier, AdBarrier achieves 70% improvement and shows better scalability on multiple cores. In real apps, AdBarrier works better than FBarrier and reduces the average latency by 18% in news, 29% in video, and 26% in SNS. And AdBarrier outperforms NoBarrier greatly in the 5 apps. The apps are listed in the bottom. In server workload, bbench is used. We use dummy command to simulate BWC, and the SSD just drops it. Compared to FBarrier, AdBarrier improves the throughput by 19% and reduces 87% BWCs in 32 threads. And AdBarrier greatly outperforms NoBarrier when threads less than or equal to 32. In this work, we focus on the basic storage order problem in computer system, and we propose Lazy Barrier to address it. The experimental results show that Lazy Barrier reduces the OPW latency in Android apps and improves I/O throughput in dbench. Thank you.
Okay, thanks for your introduction. Hello, everyone. I'm Ina, and it's a great honor to be here to introduce our work, Achieving Near Zero Re-Retry for 3D NAND Flash Memory. And this is a joint work from multiple universities. So let's get started. So 3D NAND Flash Memory is widely used for data storage in various scenarios, such as mobile devices and data centers. By 2025, 3D NAND will consume over 95% of all NAND flash memory. So the widespread adoption of 3D NAND is driven by its move toward high density and large capacity. As we can see, its structure stacks cells vertically into different layers to increase the storage density, and each cell implements the storage of multiple bits, such as TLC flash with triple level cell. So okay, when we want to read data from a 3D NAND flash-based solid-state drive, the whole read process includes 4 steps. So first, when we start to deal with a read request from the host interface, we just transfer such read command with the access address to the flash chips array. And second, we should add voltages to the corresponding cells. The latency of this process is high, about tens of the microseconds. And Next, the read data will be transferred to the ECC engine for error correction. So if the read data can be successfully read, it will be transferred to the host. However, this process is not always successful as flash chips age with program erase cycles, so leading to the reliability degradation issues. So the steps 2 to 4 will most need to be repeated. So that is, there is a performance bottleneck in reading the flash chips. So now let me show you the reasons behind from the on-chip page reading. And we take TLC flash with 3 bits per cell as example. So there are 8 voltage levels with 3 page types, the LSB, CSB, and MSB. And 7 read voltages R1 to R7 are used to separate them during the read operations. So if we want to read the MSB page, we just add a set of the read voltages R3 and R7 based on the gray code. However, the adjacent voltage levels overlap when flash ages or are subject to the retention time and disturbance. So the overlapped voltage levels increase errors and require multiple retries for a page reading. So the flash foundry often equipped with a read retry table in the flash controller to guide the retry operations. This is a part of a typical retry table, providing several sets of the retry offsets and each set corresponding to a normalized read voltage. So during the read process, the first set applies the default voltage offsets, and after data is read, it proceeds to the ECC decoding. And if the decoding successes, the read operation is finished. However, if it fails, a set-by-set retry is employed, and each retry requires a new page read operation. So the total latency can be calculated using this equation, 1 plus the number of retries, then multiplied by the read latency. So thus, more retries will cause the poor read performance. And we have collected the retry process from 3 latest TLC chips. So for each figure, the x-axis refers to the R3 offset, and the y-axis refers to the R7 offset. And each black point represents a retry offset point for the R3, R7 pair of the MSB page. And during the retries, we aim for a retry offset point near the optimal offsetting by the read dot to minimize the error rates. So for the retry orders, it's clear that some points are concentrated, leading to the overcrowded offset points, and these 2 points even overlap. So the overall retry sequence is irregular, showing a zigzag pattern, and these findings lead to the conclusion that the current chip predefined retry tables overlook the read granularity and the error behaviors. For example, the variations of retention time and P cycles for the flash page type and the 3D blocks layer variations. And then we present the evaluated retries in the traditional method and our proposal. So when no retries are necessary, the average number of page reads is only once. However, when flash requires retries to obtain the correct data, the traditional method may need many retries, even consumes over 20 page reads in some cases. So these dozens of retries greatly reduce the read performance, because the retry process of the traditional method is rigid and sequential. While our proposal consumes near 0 retry and only a very few pages need a few retries because we propose a dynamic retry method. So in the following, I will introduce how our dynamic method works, including 3 methods and a tailored retry table, an optimal voltage difference table, and a proximity search method. Now let's first discuss the development of a tailored retry table. So it's constructed through modeling and based on the experimental results. So I will introduce this process step by step. So for a page read by adding a set of read voltage such as MSB page with R3 and R7, so we can model the relationship between them. That is, once we decide the offset of one read voltage, the others can be calculated. So here we collect the optimal offset points for each page read of a 3D NAND block as shown by the blue dots. So darker the color represents more pages. So this can be formulated as a correctable read-retry cover space. So for a page with an optimal offset point within the circle, so a successful retry can be achieved by using the center offset point. And the center offset point is set to the mean of the optimal offsets for all pages in a block as shown by the red dot. So next, we simplify the cover space. So on the cover space boundary, 4 offset points within the same row bit error rate as R3 and R7 create a rectangle. So the width of the rectangle matches the R3's value window size, and its length matches R7's value window size. So next, we just use this rectangle cover space and the center offset point to guide the retry process. Okay, so we studied the characteristics of the rectangle cover space reflected by the center offset points. So as shown in this figure, for a specific P cycle, the center offset points of different retention times almost lay a straight line. And for different P cycles, the slope of each center line is almost similar. So the center point can be modeled as a linear function. So that is, we can start from the initial offset and we formulate a read-retry table that contains the offset points along the straight line and to guide the retry operations. And during the modeling process, we also studied the relationship between the value window and the retention time, and more details can be found in our paper. Okay, so next, how to decide the offset distance between 2 neighboring offset points. So the basic idea is make the rectangle cover space of 2 neighboring points overlap so that the rectangle cover space can cover all the retry space. So let me show you the process of the generating the offset points. And first, we set the value window size of 50% of the previous size. So actually, we have evaluated many values, but 50% is best. So second, the next retry point can be calculated based on our modeling, and step by step, we can get a accelerated retry table, including only 8 sets. So we have considered the retention time and the P cycles, as well as the page type. But there is another question, how to eliminate the layer variations. So the read offset of each layer in a 3D block is very different, making a set of the read offsets can only cover a few layers. So we have collected the optimal offset, and the variations among different layers are relatively consistent under different retention time and P cycles. So an optimal voltage difference table recording each layer's offset deviation from the mean allows a single set of the read-retry offsets to cover all layers in a 3D NAND block. So we can combine a accelerated retry table and an OVD table to determine the retry offset. So now we have a accelerated retry table, but one more question, how to apply the retry table? So the low density parity check code LDBC is used for error correction. So every time we read data, it will be transferred to the LDBC engine in the controller. So the LDBC code has a central value that is near linear with the bit errors. This means even when a page can't be recovered by the LDBC, we can also estimate the number of error bits. So when the error bits decreases, so the retry direction is right. By using this feature, we propose a proximity search method to find a better retry value for corner cases. So next is the experimental results. And we use a Yester platform with TLC chips, and 5 P cycles and 6 retention times are evaluated. And we also compared with 4 retry methods with various workloads. So we evaluated the average number of retries, and the traditional method suffers from a significant increase in page reads with longer P cycles and the retention times. And the existing method has some improvement compared to the traditional method, but retries are still serious as P cycle and retention time increases. So we also evaluated our proposal step by step and outperforms others with minimal retries, so approaching near zero. So next, we evaluated the performance for various workloads under different program erase cycles. So let's select one workload under 3 chips, for example, and our proposal performs close to the ideal case without retries and outperforms all other methods, especially for the higher P cycles. And then we check the retry failure rate using LDBC hard decoding after keeping the data for 10 days at 85 degrees Celsius. And the certain retry method have experienced failure rates above 40%, and our proposed method issues a 0 failure rate for up to 8,000 P cycles. So let me make a conclusion, and we study a retry problem under real flash chips, and we propose a dynamic retry method to achieve near 0 retry with high performance. So that's all, thanks, and feel free to ask any questions.
I'm Zhang Jing from Shanghai Jiaotong University, and I have a little questions that you have changed the retry table in a dynamic way. What's the cost of this dynamic methods that you need to change the retry table during the writing or reading, right? Compared to the retried overhead in the SSD.
Yeah, so the retry table is stored in the flash controller, and we redesigned the retry table. And for flash chips, there is only one retry table, and the storage cost is very minimal. And we also propose a OVD table, and the OVD table is only once. It is also only one table, and so the storage cost is also small. Yes.
Okay, thanks.
Thank you.
Any other questions?
Thank you for your talk. I'm from Kyungpook National University. If you eliminate the most read retry using your tailored read retry table.
Yes.
So in that case, you should choose the first optimized read reference depending on different endurance or retention time. For example, among in your tailored RRT,
Yes, tailored.
how to choose the first read reference voltage? For example, 1 kp cycle and the retention time is 3 months. Which is the first reference table among 8 different sets?
So actually, the set of the every page read, it depends on the P cycles and retention time, and as well as the layer variations. So we can record the value of the sets based on the last read on the each page.
You show the read reference voltage of last read.
Yeah, yes,
for
last read.
all pages, for all blocks.
This is a block granularity, and because the pages in all pages in the block are stored at a similar time, so the offset point is similar.
You mean the stored optimal read reference voltage of last read?
Yes.
In black granularity?
Yes.
Okay.
Okay, thank you.
Okay, and we'll start.
Okay, thank you.
That concludes the second European problem. So